Hello everyone, welcome to the study group on Guiding Principles for System Modeling, designed to improve your systems thinking as well as systems modeling skills. Over the next 2 weeks, we will dedicate 1 hour each day to not only learn but engage, share, and challenge ourselves. These sessions are structured to provide you with an understanding of the guiding principles coupled with hands-on examples that we will solve together. We encourage you to actively participate, ask questions, and share your experiences. Your contribution will improve our sessions and enhance the learning experience. To make the most of these sessions, please ensure that you have Wolfram System Modeler and Wolfram Desktop installed. Also, we highly recommend setting aside a few minutes after each session to reflect and practice what you have learned. Thank you for joining us, and we are excited to have you. Before diving into what this study group will cover, I would like to kick things off with a fundamental question. What defines a system? Please share your thoughts by participating in the poll. Right. So we have all of the above uh, as the winner. Robs, if you can show the results of the poll to the audience. Right. So the most votes goes to all of the above. Let's see what we mean by system in this study group. Yeah. Thank you, Robs. When we think about a system, a common example that comes to our mind is a car. Is the entire car considered a system? What about its transmission or the engine? Are those systems too? To understand this, let's define what a system is. Here are some definitions of a system. According to NASA, a system is a combination of elements that function together to produce the capability required to meet a need. The International Council of Systems Engineering expands on this by describing a system as a construct or collection of different elements that together produce results not obtainable by the elements alone. And if you check the Cambridge Dictionary, it simplifies a system further as a set of connected things or devices that operate together. These definitions reveal three key aspects that define a system. It is a combination of elements. Those elements interact with each other, and together they fulfill a specific need. In this study group, when we refer to a system, we will stick to these three characteristics. Let's apply this understanding and analyze some examples from our daily life. Consider your home budget as a system. It is composed of various components such as fuel expenses, grocery expenses, income, and so forth. These components are interdependent. For instance, allocating more money to groceries might decrease the funds available for fuel. The overreaching goal of this system, that is your home budget, is to maximize your savings, illustrating how these interconnected parts work together to achieve a common objective. Consider the task of maintaining thermal comfort in your room, an environment influenced by various heat sources such as windows and occupants, heat storage mediums like air and furniture, and heat sinks including the ventilation system. These elements are interconnected. For example, the presence of more people increases the heat generated, leading to greater heat storage and consequently a rise in temperature. By comprehensively understanding these components and their interactions, you can effectively manage and control the room's temperature. Finally, let's get back to our car example. It consists of different components like the batteries, motors, and tires which interact with each other enabling you to travel with the car. But one can also think of other systems like the transmission system that consist of components like motors, clutches, and brakes that help in delivering the required torque. So probably it would be right to say that a car is a system consisting of many subsystems. But why are we interested in systems? What is its usefulness? Consider the system for your home budget. You have already identified its various elements and how they interact with each other. Now, let's say you want to buy an apartment. This decision will add a new element to your system and change the outcome of your home budget system. By creating a system, you have narrowed down the scope of your problem, and now you can easily check the impact of your decision. But how can you check the impact? The way you can check the impact of your decision is by actually buying an apartment and checking the impact in real time. Possibly a very costly affair. What if you have to choose among 5 different apartments? Will you buy all of them? Probably not. That is where a model comes into play. Once you have identified a system, you can abstract the system as a model, probably as a mathematical model, and play with that to check the impact of your decision. For example, buying an apartment using the home budget system. To summarize, you need to define a system to narrow the scope of your problem. You then abstract the system as a model that will help you in analyzing the impact of your decision on the system. Let's look at a few examples of systems and check what type of analysis can be done. Here is an energy system that includes various subsystems such as electricity generation, electricity transmission, and electricity consumption. Such a system can be used to analyze the supply and consumption profile as well as to model the losses. One can create a model of such a system to analyze impact of changes in the energy mix. For example, how would the system behave if the proportion of solar power is increased? Similarly, here is a drone system that includes various components such as battery, mechanical structure, and motors. One can create a model and test if the chosen components can achieve the target maneuver in the given amount of time, or if the drone can transfer the payload between 2 different locations. Finally, here is a system for the spread of an infectious disease. One can use it to understand the infection curve and make decisions like determining the healthcare capacity or when to introduce a social distancing campaign. So far, we have seen what is a system, we have seen some examples of a system, and why we need systems and models. Let's now look at how this study group is organized and introduce you to the course instructors. The goal of the study group is to introduce you to thinking of real-world phenomena as systems, introduce you to the principles that will help you in abstracting those systems as models, and finally introduce you to workflows that will help you draw insights from your model that will facilitate understanding, training, and decision making, among other things. The entire study group is divided into 2 main sections. In the first section, you will become familiar with the tools. You will start with modeling with System Modeler and then analyze your models using Wolfram language. Then from Thursday, we will introduce you to the principles that will help in modeling and carry out hands-on exercises. You should have received a mail from us where we have listed the prerequisites. You need to install System Modeler and Wolfram Desktop. It is also recommended to have a second monitor that will enable you to do the exercises while listening to the lessons. The study group will be taken by me, Ankit, Vedat, and Sergio. I'm Ankit, sales engineer at Wolfram. I have been modeling with System Modeler for the past 5 years. I particularly enjoy modeling energy and social systems. My colleague Vedat, who is an applications engineer, he has a PhD in structural engineering and enjoys modeling mechanical systems and analyze impact of vibrations. Finally, my colleague Sergio, who is a software engineer. He is involved with the integration between the Wolfram language and System Modeler. You will be using some of the functions that he has developed during this study group. Let's start with today's session on System Modeler with a poll. Please answer the poll so that it gives us an idea of your modeling background with System Modeler. Those of you who have submitted the poll, they can open up System Modeler. As I said, it is recommended to have System Modeler open in a second screen so that you can follow along as I explain the model. Right. Right. So that is an interesting mix. So we have 77% of our participants who are new to it. Uh, Around 13% have used it in the past, and around 10% are current users. So most of you are new to System Modeler, and we will take that into account when we cover all those when we cover all the examples, right? Uh, yeah. Let me share my screen. Right. So you should be able to see my screen, right? Vedat, is that visible?
Right, it is visible.
Okay, right, fine. So as I said, now we will start doing the hands-on example. Uh, and before we start the example, let me try to give you an introduction of the system that we will be modeling. Uh, so we will be modeling a cooling process of a hot beverage like a coffee. So whenever you so it's a common example from our day-to-day life, which has some essential dynamics that would be interesting to model, and you can use that model to find out how much time it takes that your coffee is cool enough for you to start having it. And in this process, and in this cooling of this coffee system, we have different components, like we have the coffee mug, and the ambient. And then uh, we will model a system which would look like this, where we will have a coffee mug that interacts with the ambient, and then we will have a thermometer uh, that that is used as a sensor to measure the coffee temperature. Right. Okay. So um let's take a minute, and I would let's take a minute to open up System Modeler. And the people who have already opened System Modeler, you can open the modeling principles.mo file that is present in the shared folder. Right. Okay, so let me get started. So people who are new to System Modeler, this is the modeling interface of System Modeler, where you can see you have a blank white canvas where we drag and drop our components and create a model. And then we have different options on the top, which we will cover gradually as we move along the study group. And then you have different libraries, as you can see, the Modelica library or some other libraries that are mentioned here. And this have some pre-built components from different domains, like mechanical, thermal, or simple blocks like mathematical blocks, that you can directly make use of and create your models. But for today, we'll be using the modeling principles library, that I have created for this study group, and we will be using the coffee sub package uh, that is listed inside this inside this package, right? So the first task for this study group is to recreate the this model, is to recreate the coffee cup model using the components that are present inside this components package, right? So the task is to just drag and drop these components into the modeling interface, uh, and then we will start along. And I think I will just give 1 minute uh, so that everyone can do the task. But Vedat, did I miss anything, or do you?
No, I don't think so. Maybe you can give some hints how to start with. You
Okay.
just show the notebook, right?
Yes. So here is the notebook. So I have it here. So people can just look at it and try to drag and drop the components first.
Right, we have over there in the components like a red one and the white one. Little
Yes.
squares, what are those and such hints.
Oh,
I
right.
think that
Okay.
would be useful.
Right. Okay. So let's answer those as well. But let me start by doing the exercise myself. Okay. So let's drag the coffee mug first. Then we will have ambient, and then we will have a thermometer here. I will just zoom in my screen so that it's visible to everyone. Uh, right. Yeah, I think this should be fine.
Yeah, it is fine.
Yes.
It is
Yes.
fine.
Right. So this red things are connectors. For now, just knowing that those are connectors is a good start. Those are very rich connectors. So when you connect these connectors, they take into account the mass conservation laws, the energy conservation laws. So they are just not like input and output connectors, but they have a lot of more information about the models that makes your modeling life much easier by taking into those conservation equations into account. But yeah, okay. So now once we have all the components in place, the next task is to connect all those components. And to connect all these components, you can see we have a connection tool icon besides this arrow on the right hand side of the arrow. So we'll click that. And now our connection line tool is activated. And now we will go to the port which expands and then drag and connect it with the coffee mug. Similarly, you can connect the coffee mug port with the ambient, right? Uh, right. So we'll give a few seconds for people to um, to do this. So in this, so the idea of this session is to not to go into the thermal aspects of the different components, but the idea this of today's session is for you to get yourself used to system modeler, getting making yourself comfortable with how to drag in components, how to connect, and then how to simulate and then process the results, right? Vedat, do you have anything to add to that?
Right, we have a question.
Hmm.
Right, uh, Kabbalah is asking whether we are accounting for heat losses due to evaporation in that example.
Right.
Can you explain that a bit?
Um right. uh, so if I double click on this model, you can go deeper into how this model is built. And for this model, we are just considering conduction and radiation components. And then we have coffee storage element in it. So we are not, in this particular example, we are not considering the evaporative losses for now. So that's not the objective for this model. So we're not considering that as of now.
But it is doable thing, right?
Yes, it is.
This
It is
is
doable, of course. But for this example, I just wanted to start with the extremely easy way of modeling these things. Okay, fine. So now I think people would have completed this task so far. And if someone is really interested, they can click on each of this component, and then you could see that each component has a bunch of parameters that you can already set. And we have provided default settings for all these parameters, and one can play around with different initial temperatures and different amount of different diameters and all those things. So each of this, the ambient is a boring one. It only has a fixed temperature in it, but the coffee mug is the interesting model. Okay, right. So far we have dragged in our components, connected them together, and I showed you that you could change the parameters by clicking the components and choosing a value based on uh, what you want to model. And the thing is, once you start typing here, you can actually switch between different units here as well. So for instance, if I am not comfortable with the SI units, I can I can choose Fahrenheit as well. And then yeah, sorry, and then system modeler, and then this would automatically convert to the right unit. Okay, but so with that, what now? We have the
Yeah,
components
yeah,
in place.
yeah.
We have connected them together. What is the next step
Right.
before we start
So,
simulating it?
right, when we just get started, you ask what is the system, right?
Hmm.
And so, can we now explain that question?
Oh
For instance,
yeah,
in that one, I can say that if the coffee mug is system itself, or should we include all of them?
yeah. I think for this cooling of this coffee process, we have I think the three things together. For me, I would consider a system, because the coffee mug is interacting with the ambient, and we have a sensor to get an output from it. So and the entire the in the system, the objective of the system is to understand the cooling process
Right.
of the coffee present inside it. So I would say
So,
I would refer to a system as the entire thing with its elements, and we simulate it because it has a purpose of understanding how the model would behave, right?
right. All the
Okay.
dynamics interactions in between these components as a whole is system. You are
Yes.
saying, yeah.
Okay. Okay, so the next step is, once you have the model in place, once you have connected it, the next thing is you would want to set up the simulation, the experiment setup. For example, like how long should the simulation be simulated? So you need to specify those details for your model, and that you can do by clicking this small arrow icon besides this play button and clicking the experiment setup. So here, here you can set how long the simulation should be run. For our case, I will choose a time unit, let's say in minutes, and then I will start by choosing a stop time of 30 minutes, right? And I will just give a few seconds, like half a minute, for people to just open up the experiment setup and fill in these values, or of any value of your liking, right? um, and Vedat, you could also mention that not only the stop time and start time or the time unit, but you can actually choose between different types of solvers. You have the explicit solver or the variable step solver that you
Right.
can choose from. And also, for some simulations, we want to simulate it in real time, so it should just simulate like per second. And those type of simulations, we have options of synchronizing with real time, but those are advanced feature. But just that, you can set all those options through this window. Okay. Okay, fine. So now we have our model, we have set the experiment setup. Now we should Now the next step is to simulate the model. To simulate the model, we will just press the play button here, and let me go ahead and press it. Right. So now, once we have the model, we have simulated it, uh, we are now into the result view of System Modeler, and this view is called Simulation Center.
So
And once we have,
is this another program, Ankit? Another software?
no, this
Okay.
is uh, this is this is a part of System Modeler. So both Model Center and System Modeler combined, uh, we both Model Center and Center combined, we have the System Modeler product. So it's a part of uh, System Model. It's not a different tool. Uh, right.
Yeah,
Okay.
thanks for explanation.
Yes. Okay. Right. And then uh, I did cheat a bit, and and the thing I cheated was, I already saved the plot in my model. So when you guys would also create simulate this model, you'd have got this plot here. But usually, when you simulate a model, you get to this blank plot screen, and then with this different options like plot, parameters, and variables. So once you have a model, once you have simulated the model, the next thing would be, you want to see the different values of the variables, and that you can do by going to this plot tab, right? And this plot tab lists all the different, unfortunately I cannot zoom in this view, but this plot tab lists all the different components present in our system. For example, we have the ambient, we have the coffee mug, and we have the thermometer. For this case, probably what we want to do is we want to model the temperature, right? We want to model the temperature of the coffee, of course, and then we can open up the thermometer component and the temperature sensor component, and then plot the temperature here, right? I think I would give like a minute or so people can actually try it for themselves. So what I did was I created a new plot. uh, I think for some people they would have started with this plot itself, but if you want to create a new plot, click on this icon on the top left icon here, which says y comma t, which is basically the variation of a variable with respect to time. Click on that plot, you will end up with a blank plot, and then you can select which variable you want to plot. And in this case, I have plotted the value of temperature sensor here. And if you are not comfortable with degree centigrade, you can actually change the units to degree Fahrenheit as well. We are in Europe, so we are used to degree centigrade, but you can choose between uh, the different units here. Right. Veda, do you have anything to add up to this point?
So far, so good. So maybe a philosophical question. So why are we using System Modeler? Couldn't we do the same by using an Excel? So why do we need this
Yes.
tool to?
Okay, so there so there are different lot of reasons, and right. So okay, the first reason, of course, is you're solving this like differential equations, or the ODEs, and you have events, which goes more technical into which goes into more technical related answer. But you have the states, and then you want to see how the different states of a system, they progress over time. Also, you would want to have events. Also, you would want to have components, so that you can document them together, and when you're presenting it to them, you can see the model as different blocks, which and each block does a specific job, right? So it's much easier to consume a model. But if you do all those complex mechanism in Excel, then if you think of sharing your Excel model with someone else, it it is
Yeah, it will.
it
It
is
look
very
like
daunting.
gibberish.
It is very daunting, at least for someone to whom you're sharing. And just understand, if there is some error, how would you troubleshoot it?
Right.
So it gets tricky. Okay,
I
then.
get we have a question about the blue filling.
Oh
Uh,
yeah, okay, so I have a global setting for it. Okay, so the thing is, so let me get back to the default setting first. Go to general with the plot options. Yes. Okay. So I think most of you would have got a plot like this without a filling. And if you want to have some filling in the plot, I find it useful, because if there is a zero crossing, then it helps me to easily identify it. And if I plot multiple plots, it helps me to segregate them. So I kind of I have set this plot themes in the global properties, so I don't need to define it all the time. But if you want to play around with different themes and try to see which theme suits your model, you can actually switch between the different available themes here, right? Okay, so now once we have the model, you have simulated it and plotted the results. The next thing that we should do is, let me see, what did I write? Okay, so the next thing is, once you have the simulation, we started with a random simulation time of 30 minutes, right? And in most of the cases, that time is not what we want. It's just the first guess value that we have to give, because we don't know the dynamics yet. And in this case, let's say if you want to simulate it for longer, then you can go to the settings, and in the stop time you can simulate it for a longer time. For instance, I have selected 60 in this case, and then press on the simulate button here. And when you do this, you see that my temperature, my time duration has changed. So once you have the plot, this is the first thing that I typically do, right? The next thing that you would do once you have the plot is, you want to test different scenarios. Like, what would happen if my ambient temperature is something else? Or what would happen if my initial temperature is something else? How would you test those scenarios? Do you, like, should you go back to the model, change them, and then simulate again? Of course, you can do that. But the easier way is to just go to the parameters tab and then change one of the parameters. For instance, I want to change my ambient temperature to, let's say, 15 degrees centigrade. And then I will click simulate. And now you could see how my temperature has changed. So you can quickly iterate through various uh, parameters, or test different scenarios by changing the parameter values here. And finally, let's say, so Vedat, there are two things. We have a parameter and we have a variable. How do I distinguish between what is a parameter and what is a variable?
Right. Maybe I can answer that.
Yeah.
So now in this example, what we had a coffee mug, right?
Yes.
In this coffee mug, we are interested in the temperature over time. So which is the variable changing over time? But the parameter is something doesn't change over time. When we initiate the simulation, we are saying that this thing will constant. So that is how we define parameter. That is also constant definition. It is a advanced topic. We will come to that. I don't want to mix things up.
Okay.
Right.
So what you mean to say is, since our temperature is changing over time here, it is not a parameter, but it is a variable, right? And then let's say if I want to change the initial value of my variable, then I can use the variables tab and perhaps go to coffee mug, maybe coffee, and then I can change the temperature here. Maybe let's say it was, let's say, 80 degrees centigrade. And then I can simulate again. right. And for some reason I have this one. Let me delete this. I will I will get back to this, but for now let me delete it so I don't override those parameters. Uh, right.
Ankit, maybe we can also increase the time and show uh, what is the steady state temperature of the coffee mug, how far,
Okay.
how cold our coffee mug can get.
Yeah, it is. I think so. Yeah. So this is the. Let me simulate for longer time. 180 minutes, and then you can see that I'm getting to 15 degrees. So the steady state temperature is of course the ambient temperature, and I can get the value either by hovering over the variable, or I can press control and then click on the time axis, so I can get a measurement at that point in my measurement window here. So here you can see my the temperature after 150 minutes is 15 degrees centigrade in this case. So if you want to have want to have different snapshots of time, you can actually control and then click on the x-axis, and you will be able to plot those variable. Right. For some reason, Vidat, my coffee temperature is not changing, but I think we can I can look into it later on. Right. Okay. I will have a look at it later. Uh, okay. So getting back to the model.
Mm.
So once we have the plot, um, we can change the parameters. We can change the initial value of the different variables, and we can change the experiment setup like the stop time and so on. Right. Right. Okay. So now the next thing that okay, Veda. So what should be the next thing? Now, once we have the model, we know how to test different design scenarios. What should we do next?
What will be interesting now? Okay, yeah, good question.
Okay, but I think before we discuss any of the what should we do next, we should try to store our plot in the model so that next time when we simulate uh, our model, we get back the plot, right? So we don't have to recreate the plot again and again.
Right,
And
right,
so
yeah,
now let me try to show like how can we store our model for our future usage. Or if you are trying to share your model with someone else, you don't need to tell them which variable to plot. You can already plot the variable that you want, save it in the model, and then you can easily distribute to others. So okay, so to store that, you have this not stored option on the top right here. So I will just press this and say add plot to model. And when I click that, I can give it a title, my new plot, and make it as a default plot and click OK. And when I do that, my new plot is added to the model plots. I think,
so you click there default plot
yes,
there. So
yes.
what was the reason of that?
Okay, so, right. So let me delete my previous plot here. Okay, just to repeat the step, I will just remove this. You click on the not stored thing, the not stored text, and then you click on add plot to model. And when you get the add plot to model, you give it a new title, and then you can choose either to be a default plot or just to list the plot here as a not default plot. So the default plot is, let's say when you simulate a model, which plot should be shown at the start, right? If you
Oh,
have
I
five different plots stored in the model, all five should not be shown. It will be very confusing. So you can actually select which plot to show first, and then you can have auxiliary plots, which are not the primary plot that you want to see, but those plots help you in your analysis, right? Okay,
right, yeah.
okay, fine. So once you have a model, we have simulated it, we have plotted it, we have now stored the plot. I think I should give a few seconds for or a minute or two, so people can actually try to to play around saving a plot, because I think saving a plot is quite often missed in the modeling process. But anyways, let's ask Sergio. Sergio, where are you, man? Do you have anything to add on what we are discussing so far?
Right now, I've just been answering questions.
Nice.
um, yeah, we've had people asking about uh, the thermometer in the icon. Uh, they were wondering if it should be blank or white because um, you kind of expect the temperature to rise or
Oh, here.
yeah.
Uh, so there is a concept called dynamic diagrams,
Hmm.
where these diagrams also get automatically updated depending on a value of a variable. And of course, you can create such interactive diagrams using, but you need to use Wolfram language for it. So you create a model, and then you can actually check the diagram in Wolfram language where these things would vary. You would have a time slider, and then this diagrams would vary, and that is
Right.
something called dynamic diagrams. If we would have time, perhaps Sergio, you are the best person to give you an to give an example, but not today. Maybe
Hmm.
sometime during some other session, or we
Hmm.
can post a small example in the uh, in the community, so
Right.
people who are interested can actually see that example.
Hmm.
But yeah, that's a interesting question, and of course we have thought of a solution, but that solution would need uh, currently would need Wolfram language as well. Okay, right.
Yeah, Ankit, can you answer also why we have red dots, red connection dots, and the white ones for the ambient? Why they are different?
Oh, um, right, right. Uh, Vedat, I will get back to that. I have one more thing that I want to cover
Okay, yeah,
in this view, and then we will get back to Model Center. Is that okay?
yeah, yeah,
Okay,
sure, sure.
fine.
We are
So,
all here.
fine. So the final thing which I want to cover, and I think this was also, um, if you'd have used the modeling principle, step one um, uh, model, then you would have got this things by default, which I had already added before before I did this. But if you want to add a model parameter, okay, fine. So that we have seen so far that if you want to set a parameter value, the way that you do it so far is you go to this value and you change, right? You change the value here. But let's say if you want to just play around with with different values, it is cumbersome to manually type those values again and again, right? It would be
Right,
nice to have some kind of a interface where you can just like a manipulate in the Wolfram language, where you
right,
can just
like a
drag the
slider.
slider and play around with the different values. So let's do that. To add a control object, we click the plus icon over here, and then we select the control object. Once we do this, we all the components present in our model are listed. And in this case, let's have the ambient temperature as a slider, right? We will attach, we will vary the ambient temperature using this slider.
So this ambient temperature is a parameter, right?
Yeah, this
Which
ambient
we can,
temperature is a parameter, but it can also be initial values. So you can
right.
change between parameter and initial values using this interface. And then either I can get the label of the parameter which I have defined uh, in the model, or I can write my own uh, label for the slider. So for instance, yeah, ambient temperature, not coming up with anything unique. Okay, no, I will say my room temperature. Yeah, okay. And then in the control type, you can select between either you want to have it as an input field, a slider, or a pop-up menu. For us, for now, let's take a slider and change it between, let's say, 10 degrees centigrade to 40 degrees centigrade. I come from India, so it's hot also. Okay, so now and then you can switch between linear and logarithmic, but we will. check, we'll keep the linear option for now and click OK. And now you could see that we have created a new control object, and this control object is saved in the model. So when you share your model with someone else, they will also, if they have system modeler 13.2 or 3, I don't remember exactly, if they have a system modeler with a higher
13.2, I
version than
guess.
that, then they can have this interface already built in, so they don't need to recreate this, or you also
Ankit,
don't need to recreate this. Yes.
Ankit, can you tell us how we can get there?
Okay.
Because
Yes. So we go to the explore tab on the first, right? And in the
right.
explore tab, either it says create a new panel, and then you click there, that option. For now I have a panel, that's why I'm getting this plus option here, right? If you start with a blank, you would have got a message saying you can create a panel by
Mm-hmm.
something something, and then click somewhere in the first tab. Or if you already have this panel done, then you can add a control object by clicking the plus button here and then selecting control object.
I see. If we don't see Explore tab, then we can say that that version doesn't have the
Yeah, I
similar.
think
Okay.
yes. So uh, I think so. I think that
Mm-hmm.
would be the right analysis. So I think to for this study group, uh, people can try with the new version of system modeler, that is version 14, because that has a lot of new functionalities that we might cover in the study group, like dealing with units and other things. But yeah, so I created this model taking into account version 14. So that is my expectation, and some people might find it a bit different if they're using an older version. But yeah,
Right.
this is version 14 that I'm using, right? Okay then. So far we have seen to plot, we can uh, store the plot, and then we can change the parameter, variables, or settings, and then we can add a slider to one of the parameter and quickly iterate through various designs quickly, right? Okay, now let me get back to model center. Um, right. There are a lot of things that I want to cover here as well, but I will not go any further because we have 8 more sessions coming up. So if you don't understand something, it's very normal to feel overwhelmed at some stage. Just try to give yourself some time, and once we are done with the 9 sessions, I think one would really be comfortable in using this. Okay, right. Uh, okay, so
We had a question
yeah,
here,
yes,
yeah, from the audio, and they were asking what is the difference between this red one and the white little squares, connector squares.
yeah. For this model, nothing. For this
Okay.
model, or yeah, for the thermal models, nothing. It's just a visualize. It's just different ways of visualizing it. But it doesn't matter. See, here I'm connecting a red with a red, and here I'm connecting a white with a white. That doesn't mean that I can't connect this white with this red. For the thermal domain, it's just for visual representation, because sometimes you have elements with a notion of coming in, coming out. So sometimes it help when you have a component with in and out, it helps you to visualize it properly. But since the connectors are based on equations, right, and those equations actually determine whether something is going in or something is going out,
Okay.
we use concepts similar to Kirchhoff's current law and Kirchhoff's voltage law, and use those concepts in determining um, how the connectors are connected. So at least in this in this example, in the thermal domain, uh, they don't have any different. It will not differ.
Okay. Okay. Can we say that in built-in components, like the Modelica standard library, maybe we might have an approach. If it is like a source, then it is red. If it is sync related component, it might be white. I am not sure, just speculating.
No, I think it depends on
Mhm.
because you have different domains, and it might differ. I cannot say a
Okay.
generalistic answer to
Yeah.
I can give a
Yeah.
generalistic answer to that. Okay, with that. So now we have seen the model, we have plotted the results, and then we have played around a bit. The next big thing, and I think the most important thing, once you are done with the model, is to write some documentation, right? So, so the thing is, so once we are done with the model, you want to write some documentation so that if you get back to the model after, let's say, 1 month or 10 day, 15 day, you want to know what was in your mind when you started creating this model. Like, what were the assumptions that you made? What were the future add-ons that you wanted to add to the model which you have not done yet, right? And so those are the critical things. And also you want to give references. Okay, you use this model, but you followed some principle or some example case covered in some other text, and you want to refer it to it. So that's why adding documentation is important, right? Now let's add documentation to our this exercise, to this one. To add a documentation, you simply right click on the model and you go to this view class documentation, right? So right click and view class documentation, and this will create the documentation of the model, right? So I will give a couple of seconds, so people to at least get to this stage. So you right click on the model, click view class documentation, and you will get this view. And in this view you can see that system modeler automatically pre-populates your documentation with some data. Like, it lists the name of your model. In this case I didn't have a description, so it's blank, but it also shows the diagram of your model and then the different components that are used in the model. So we do try to automatically populate uh, some of like your documentation. But now let's say you want to add the objective of your model, and how can you edit it? To edit this document, you click on this small arrow here, besides this the pen option here. So here, so I will pause here for a couple of seconds so people can actually see it. So you click on this small icon on the top bar, and then you will be provided with different options like edit information in what you see what you get editor, or edit information in HTML. Some of my friends or some of the modelers I know, they try to work with HTML just because they could style it as they want. But I personally, I just for me, the what you see what you get editor is good enough, right? So what I did was I opened the documentation and went to this edit information in the what you see what you get editor, so the first option. And once I get go there, I can then use I can then edit my text, or I can use a different
Styling.
styling styles, and then I can create uh, my documentations. For example, references, uh, uh, example example documentation from somewhere.
Alright.
Okay. So you can feel free to edit how you want it. Basically, when I create a model, I try to write the objective, like what was the goal behind this model, like what was the thing that I was trying to analyze using this model. And then I also list what are the assumptions. For instance, here I have written that the heat transfer by convection is neglected. So I'm neglecting that you're not drinking coffee outside and there is no wind blowing. I'm considering that you're inside a room and there is no wind blowing, so there is no convection. And also, for the coffee, I'm just considering the heat transfer parameters for water. So if you add coffee, perhaps the heat capacity would change or some other parameters would change, but I'm not considering that in my model. And that's why I'm trying to list it that I have not done it. Maybe in the future, I would like to edit it and update that as well. But for now, I don't want to do it, right? So you can list all the assumptions, and then you can click back on the same icon. So if you click back on the same icon, you see that in the information your text is updated, right? So we'll give a few seconds to people just to try it, and try to get used to the documentation. And once you are done, you can close, and then you can just you can save your model. And the next time when you open, you have the model plots, you have the control panels, and you have the documentation stored in the model, right? So with that, I think we are crossing the time, but before,
Right, right.
I
Uh,
would get back to my presentation just to complete what I thought I would cover, and then we can take questions so that people who have to leave, they can leave, and people who want to stay, they can stay, right? Okay.
right.
So in this presentation so far, we covered a simple yet powerful example of cooling of a coffee mug of system. But of course, system modeler can be used to do much more advanced models. Like in this case, we have a building with a heat demand, or with an electricity demand, coupled with a battery pack and solar panels. For now, this looks like cool icons, but trust me, inside these icons there are 5 or 10 different layers or hierarchies with electrical models. So you can create
Ankit, let me interrupt you there because that is related to a question we got. So we got the question of how the system modeler know that we haven't a linear temperature decay. So we show that something first order degradation decay. So how we get that dynamic? So I guess under the hood, it would be nice to just give an overview how those pre-built components are written.
uh,
So it is like a
yes.
magic box now. We just drag and drop things and
Yeah.
show the magic.
I completely get you. And of course, when I started modeling, those were the questions that I had. But we have 8 more sessions coming up, and the
Right.
objective of today's session was just to start with getting used to the component, drag and drop, and then getting used to the plot. We will be covering all those questions as we go along. But if someone is really curious and cannot control their urge, they can double click on the coffee mug, they can double click on the conductance, and they can open the class. And here you can, on the top bar, you have the text view. And in the text view, they can actually read or go through all the equations. And the thing is, this code that you are seeing is not a Wolfram specific code. This code is called Modelica language, which is also a different tangent. I don't want to go now. But
Right.
for people who are really curious and you cannot wait, so all these models that we have created uh, are made using the Modelica language, which is an open standard language for modeling this kind of complex physical systems. And this equation are as a simple equation that we are used to. This equal to is not an assignment operator, but this is just an equation. uh, so people who really want to understand how these components are built, they can go to the text view, they can look into the equations. Also, if you're eager about Modelica, you can search for Modelica and know more. But along the coming 8 days, we will also be trying to will show you eventually what this code looks like, and if you want to do more complicated models, how you can do. But we will go slowly, right?
Right.
Okay, fine.
So we cover all the dynamics related to that domain in those components already. That is why we are seeing that
Yes.
result. Yeah.
And also, if we have our own custom equations, we can create blocks for our own custom equations. But that is another tangent. I will wait for tomorrow, because
Right.
I'm going to show it tomorrow, that if you have your own equations, how you can create your block out of it using the Wolfram language, which we'll cover tomorrow. Okay, anyways, let me finish it first. So yeah, you can make energy models and try to understand or try to yeah, test your logic, like if the battery is sufficient to power a building, for instance. Or you can use a drone model, a very comprehensive drone model, and try to understand what is the effect of wind. Is the controller sufficient to uh, the controller that you use to let's say hover a drone at a particular height, is the controller sufficient to maintain the position at that level, or is it not sufficient? So those kind of control related questions you can answer by creating more realistic models. And also of course you can create an animation uh, using um, system model. That feature I have not shown it today, but there are some components where you can actually add animation to your models. So rather than just plots, you can actually visualize the multi-body uh, objects in the animation view. Yeah. And finally, this is a topic which we will cover, I think, in the third, in like on Thursday. We will be modeling a simple a spread of an infectious disease, and we will be trying, and using that you will learn how to create some uh, this uncertainty plots, like if some parameters are uncertain, how you can like how would the model behave for those kind of uncertainties. So you can do much more complex models with system modeler. And in the coming eight sessions we will go into more detail and try to cover different types of examples. Right. Okay, Vedat. Now I have covered what I thought I should cover, and now uh, if there are any questions, please shoot at me.
I guess we don't have any question left. Um, Maybe you can also quickly show us how did you come up with those nice figures. So
uh,
that is
I
also that is also
um,
part of the model, right?
yes, 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 yes. Okay, nice picture. So that's proprietary information. No, no. Okay. So the thing is, once you create a model, create a component, and this is something we will cover later on, but I'm just trying to cover it now. So once you create a model, you can give it an icon of your choice. So on the top, we have this model view. On the right hand side, you have the text view. On the left hand side, you have the icon view, as you can see here. Unfortunately, I cannot zoom in into this part, but you have the icon view here. When you click it, then you can have what this shows is the icon with the grid on. Let me just remove the grid. Um, View show grid. Yeah, and in this icon view, I have attached an SVG. So I got an SVG uh, from open source, or you can create your own SVGs or your PNGs, and then you can have your image in the icon. In this case, I just used an SVG. Or you can use the different drawing tools. You have rectangle, you have the basic drawing tools, rectangle, ellipse, polygon, or a text, and then you can create your own icon. um, like I know like some of our users are very strict with icons. They have their own logo in the icons, as well as color. The color coding is also based on their company and all. And this we will try to cover later on. But yeah,
Mhm.
of course, if you want to give more life to your components, you can add icons to it. But so far we have not covered components, so so people who are new to system modeler, please don't get confused. uh, this is something advanced. As you start using system modeler, we will introduce you to the concept of components in one of the sessions. But for now, just know that this is possible. Yeah. Okay, Vedat, is there any more questions that we should answer?
I guess we are done. Pretty much those were all the questions. I don't know, Sergio.
Yeah, there is a
Have we
question
missed
that
anything?
uh, what is a system? Is all of the above correct? I think all of the above is correct. Like in the first we had, what is a system, right? It's a collection of collection of elements that interact with each other, and they have the objective is to meet a demand or meet a need. uh, right, so this is the, so I think what what people say is right. So all of the above
Right.
is the right answer for that. Okay then, so if we have no other questions for today, then I think we are done. Sergio or Vedat, do you guys want to add anything?
No, I guess
Okay.
pretty much done.
No, I guess we're seeing also a lot of interest on how you can export the simulation results.
Mhm.
Um, but I guess we will cover also in, well, in different sessions. So yeah.
Right. I think those are really good questions, and I think we will try to cover or try to answer in the upcoming sessions. Yes. And if you have any questions, as Cassidy said at the start, please try to post it in the community chat, and we will try to respond to it whenever we have time. Yeah. Okay. Thank you, and thank you for today. See you tomorrow.